The ATV, in the same way as the Progress ship and the Japanese H-2 transfer vehicle, the automated transfer vehicle will be commanded to a destructive entry into the atmosphere, and the surviving pieces will fall harmlessly into the ocean. It is used as a trash disposal vehicle when its cargo delivery work is complete. Now, NASA TV viewers have heard us use those words many times in discussing the disposition of cargo vehicles, talking about a destructive entry over the ocean. Well, it turns out that simply disposing of a vehicle in this way isn't always good enough. Knowing how one of these vehicles breaks apart while it plunges through the atmosphere is of value too. And the space station's science program has an investigation that's designed to learn more about that. It's called the ReEntry Breakup Recorder. And Aki Hoshide activated and installed the REBR hardware in ATV-3 this morning for the ride back down after the undocking coming up tomorrow afternoon. The principal investigator for the ReEntry Breakup Recorder is Dr. William Ailor, and he joins us this morning from his office at the Aerospace Corporation in El Segundo, California, to talk about it. Dr. Ailor, tell me when and how you got interested in the question of finding out how things break apart when they're coming in through the atmosphere.
Certainly. Good morning. I joined the company back in 1974, and shortly thereafter we had the Cosmos 954 reentry that left some debris in Canada. And then sometime after that, again, we had Skylab that came down, and that also, there was concern with things breaking up in the atmosphere. So I got interested during that period and have sort of followed this particular topic for a long time.
It's maybe a too simple a question to ask why it matters. I think it certainly matters if this debris is falling on my house as it entered, but is there value in general of knowing how a spacecraft is destroyed?
Yes, indeed. Basically, we have a number of large object reentries that come in. These objects come in randomly every year, and these objects that come in randomly can be large enough to cause, hazards on the ground, and the so that was one reason we want to know why things break up, is to know how to assess that hazard. And assessing the hazard is interesting these days, because one of the ways for removing space debris from orbit, or removing it as a concern, is to re-enter it into the atmosphere. And there are basically two ways to re-enter things. One is to do it like we're doing with the ATV-3, which is directed into the ocean, but that can be expensive for somebody who's operating a spacecraft. So if we can lower the hazard sufficiently for these large objects, they could be allowed to re-enter randomly, and that reduces the cost substantially for spacecraft operators.
Generally speaking, how large does an item have to be in order to survive all the way to the ground?
Well, basically, the way we assess this is experience tells us that anywhere from 10 to 40% of an object's dry mass on orbit will survive to hit the ground. So that means that you have to have an object of sufficient size that has big enough surviving fragments to be a hazard. I would say the general rule of thumb is anything that weighs more than about 800 kilograms is probably something that we would be concerned about.
And some pieces have survived. Does studying them tell you anything about how the spacecraft disintegrated?
It does indeed. As a matter of fact, we have a program working with our local Air Force to bring back surviving things that are found on the ground that have survived reentry, and we do a metallurgical analysis on those to try to understand how hot they got, and we compare those results to what our models predict.
So you can learn some things, but I take it not as much as you'd like to know.
That's exactly right. Basically, what we'd like to know is, what altitude do things come apart? What is the heating? There's some evidence that the models, at least prior to this time, have been over-predicting the heating at high altitudes, which means that you would predict that less survives than actually does. And so one of our objectives with this ReEntry Breakup Recorder is to get some definitive data on how objects respond as they re-enter the atmosphere.
Okay, let's talk about the hardware. Can you describe the REBR, Reentry Breakup Recorder?
Sure. Basically, REBR is it's about a foot in diameter, about 9 inches tall. It weighs about 4 kilograms, or about 9 pounds. And the way to think of it, it's basically a cell phone with a heat shield and its own little instrument suite. So basically, the way REBR works is it sits inside the host vehicle. It's in a copper shell. As the host vehicle reenters, the aerodynamic heating will break apart the host vehicle, expose the copper shell to heating. When that copper shell gets hot, there's some plastic bolts that melt away, and it releases our little device, the ReEntry Recorder, which through the reentry process records things like accelerations and rates and attitude rates, temperatures, pressures, those types of things. And so when we get released, and after we're free flying, around 60,000 feet or so, we're basically falling straight down, and at that time we make a phone call on the Iridium system and dump our data.
And when you say released, your thing turns into a satellite and is left flying on its own because the vehicle it was in has destroyed itself around it.
That's correct, exactly. Yes, we're buried inside in that trash pile you described. Not quite like that. We're actually strapped up near the hatch. But as the vehicle breaks apart, we basically count on the fact that everything inside is going to be released due to the aerodynamic heating as the outside structure is melted away, and then of course then we get released, as you say, and we fly separately.
You're thrown clear of the wreckage.
Thrown clear, exactly.
And the data is delivered how?
It's a Iridium call. It's a call on the Iridium system. It's basically satellite telephone, basically, and we make a phone call. It goes up through the satellite, comes down to a web page that we can access from our desk.
Does the REBR itself survive?
REBR does. As it turns out, we didn't design it to survive impact, but in the last several reentries, it's actually landed in the water in the South Pacific, and it's continued to broadcast for a number of hours. Those can be expensive telephone calls.
You haven't recovered one?
No, they're not really designed for recovery, and where they come down right now is in a very remote location. But we do have information on the back of contact information, so if somebody finds one on a beach or something, they can tell us.
You say that they've come to, how many have you flown so far?
We've flown 3. We flew one on HTV-2. That was successful. That was our first one. We flew one on ATV-2. That was not successful. And so we flew one on HTV-3 just recently this month. It came in earlier this month. Worked beautifully, and we're hoping the one on ATV-3 will be successful.
You simply didn't get the data from the last ATV, or?
That's correct. We simply didn't, and we have a number of theories as to why that might be. We were located near the propulsion system on that one. Previous reentries of that particular one had a fairly violent breakup, including an explosion that could have damaged our systems. We did a lot of testing this time to make sure that we're rugged, to look for any faults. We did fix a few little things that could have caused trouble too, so we think these are much more robust this time, and we're hoping for success.
What have you learned from the 2 sets of data that you did get?
Well, we got very good information on the attitude during the breakup process, how the spacecraft itself responded. We have good information now on the breakup altitude, which has always been something that's of great interest because the breakup altitude, in a sense, defines the ground footprint, which is where all the debris will land. Again, that's another important factor. And we basically watched, so we're able to detect a few events as we were coming in. One of the problems with our current device, or limitations I should say, is that it really has its own internal sensors. We're working on a device now which would record data from a number of small wireless sensors that would be placed in various locations in the host vehicle. That will really provide superb data for doing the type of work we do. And
with an eye toward applying this to future spacecraft or better designs of existing ones?
Indeed, yes, exactly right. We basically would be able to do something called design for demise, which it means that you could design a spacecraft with features in it so that it would come apart in controlled ways, hopefully limiting the hazard on the ground. And you would have some confidence in those designs because you can have a nice way of testing those. As a matter of fact, one of the potential uses for these types of devices is as a black box for commercial space transportation systems, so that you can record what happens in case there's an accident. You can also use these devices for testing heat shield materials, which in fact we have sensors in our heat shields on this one, and they provide some very nice data on the temperature distributions in the heat shield.
You have one that's flying, as it were, tomorrow. Are there more in line?
Yes. Well, let's see. We have an internal research project on this wireless version I was talking about, and we're trying to find the funding to build and fly those. There's a lot of interest in flying them, but we need to build a few. So hopefully we'll be able to get some funding to do that.
And but everything is now set for this one to come down with the ATV tomorrow.
Yes, indeed. We're all set. I think it'll be very nice. I believe it's Wednesday night, though. But yes, we are looking forward to that particular reentry, and it'll be quite exciting, I hope.